In the last video in the series, we turned a world anvil world into a graph. These worlds are a collection of articles that have references to other articles within them. By representing each article as a node in the graph and the links between articles as edges, we were able to construct a graph that represents this world. Now that we have the graph, we need to figure out how to get some actually useful information from it, so that we can figure out the best way to interact with the world and in which order to read its articles. There are two main ideas to explore here. One of them is bottom up, while the other one is top down. Imagine the world in question as a pyramid. At the top of the pyramid there are a few broad articles, summaries, chronicles, histories, or stories. At the bottom of the article are the most specific articles, definitions, individual locations, individual items, and characters. In a top-down ordering, we read from the top of the pyramid to the bottom. It is a general first approach. This is arguably a more natural reading of the articles within a world, because it starts with the overviews or summaries. It is the way that most stories are presented. Movies don't start with the explanation of some obscure fact or location, but with scenes that establish the world in general. Alternatively, we can have a bottom-up or specific first ordering. This ordering builds on the most fundamental pieces of lore to build up to complex histories. In an actual story, this would make little sense, because there would be no mystery to unravel. Everything would be known before any mystery can even be introduced. However, it could make for a less confusing reading order because of this lack of mystery. The interesting thing about this bottom-up reading order is that it reduces the number of times readers encounter a link to something they haven't read yet. This could reduce the number of times readers lose themselves within the weeds of your world, since they have likely already read those articles. While our graph does not understand the contents of the articles in terms of their generality, it does know what connections the articles have. Using only the links of the articles, we can define two useful quantities that are represented in the graph: the in degree and the out degree. As the name suggests, the in degree of a node is the number of edges pointing into it, while the out degree is how many edges it has pointing away from it. For our purposes, we will assume that the most general articles have low in degrees and high out degrees. They reference or allude to many articles, but are referenced by few. In contrast, we assume that specific articles are referenced by many other articles, but do not themselves reference many. These articles form the bedrock of the world, and are where the discussion reaches its end. Using these concepts, we will generate both a bottom-up and a top-down ordering, by using an algorithm similar to the topological sort. A topological sort is an ordering of nodes in a graph so that, for each edge, the node where the edge originates always occurs before the node where the edge terminates in that ordering. Let me give an example. Imagine we have the following layout of articles as nodes and links between articles as edges. Using a top-down approach, we have to read the country article before the city article, and the city article before the building article. This ordering is trivial, so let's add some more articles. Now the nodes are still laid out in order vertically, but horizontally it's a bit more complicated. Working through this by hand is not too complicated though. Here are a few valid orderings of these articles. Note that there are multiple valid orderings. As we saw in the last video though, graphs created from wikis are not this linear. There are often edges back and forth between articles. This makes a topological sort impossible, and it's easy to see why. These edges will always flow in the opposite direction of one another in any ordering. In practical terms, this means that we have to read the city A article only after the city B article, which we can only read if we have already read the city A article. We have to read the city A article before we're allowed to read it. Because of this, topological sorts only work on acyclic graphs, such as the first example I gave. However, we can use the general idea of a topological sort to come up with a more general algorithm that can handle cycles. Our solution is analogous to Kahn's algorithm, so let's look at how that works. In Kahn's algorithm, we start with the set S of nodes with no incoming edges. We remove a node from the set to analyze and call it N. Since this node has no incoming edges, we know that we can add it to the ordering. We then look at each neighboring node M and remove the edges from N to node M. We look at M after removing these edges and add it to S only if it has no more incoming edges, so if its in degree is 0. We repeat this until we have added every node to the ordering. In this algorithm, we put nodes in our ordering only when they have no more incoming edges, but the cycles in our graph make this impossible. Instead, we shall add nodes with the lowest in degree to the order. Not a node with 0 degree, because that may be impossible, but the node with the lowest degree. If they are ties, we add the node with the highest out degree, because that will reduce the in degree of most other nodes. On a graph with no cycles, this algorithm will produce a topological sort. And on graphs with cycles, it will produce an approximation of a topological sort, a kind of pseudo-topological sort. Armed with this strategy, let's get to coding. First, we'll need a graph. To generate it, we can use the code we wrote last time. We also compute the transpose of this graph. A pseudo-topological sorting of the graph will produce a top-down sorting, while the pseudo-topological sorting of the transpose will give us a bottom-up ordering. As discussed in the previous section, this algorithm adds one node at a time to the ordering, so let's write a function to do that. We write the function getAndRemoveNode, which takes a graph and an array to hold the order. To select a node, we need in-degree information, so we get that and sort it from lowest to highest. We select the lowest degree for future reference. Remember that there could be many nodes with the lowest in degree, so let's find all those. Of those, we want to find the one with the largest out degree, so we iterate through the list and keep track of the best node we've found so far. We add the best node to the ordering, along with its title and its in degree. In an ideal topological sort, this degree will always be 0. We then remove the node from the graph and return the in degree of the node. This is the algorithm basically done, we just have to repeatedly call it on our graphs. We set up an array for the ordering and a cost that holds the total number of in degrees we added to our ordering. We do this for both the original and the transpose. Now we call the function to add nodes to the order until there are no more nodes left to add, keeping track of the total number of in degrees added. Again, we do this for both graphs. For future reference, let's output these orders to a text file. Without explaining my articles, I can say that the original ordering makes sense. Summary articles are placed near the top, along with narratives and mythologies, and brainstorming articles. Unsurprisingly, the opposite is true for the transpose sortings, where summaries are placed at the very bottom of the ordering. If you are doing this for yourself, try changing the greater than to a less than in choosing the very best node, and see how the total cost of the sort changes. It should verify that choosing higher out degree nodes was a good choice. I wonder if this locally optimal choice would lead to the globally optimal solution. Try coming up with a graph where a different secondary criteria would give a better lower total cost, and leave it in the comments if you do find one. An interesting thing to note is that independent articles without incoming or outgoing edges, which are probably articles that are unfinished, are located near the beginning of both the original and the transpose orders. This is not too difficult to reason out. What would be quite interesting to try next is to only allow for edges between nodes that obey these orderings. This would break any cycles in the graph and will hopefully lead to a very appealing visualization. Thanks so much for watching this far. The links to the previous video and the GitHub repo are in the description. Since this is an open source project, I would encourage anyone watching to dig through the code, apply it on your own worlds, and even improve it. Please feel free to send in a pull request or leave improvement ideas in the comments. I know there are many ways this can be improved. For example, this algorithm is horrendously slow. Just calculating the in degrees and out degrees is big O of E plus V, and we're doing that exactly V times. This makes the final runtime big O of V squared plus EV, which is V times slower than the traditional topological sort. I could make this faster by not computing in degrees for every node, but this would require that I use a min heap with a decrease key function, and I think that's too complicated for a video like this. Like last video, there's an interesting discussion to have about the creativity of using a tool like this. Obviously, it would be more creative to manually construct a reading order instead of outsourcing it to code, but I don't think it's worse because of that. I probably wouldn't have ever made a reading order if doing it manually was the only option.